All right, so welcome back to this channel. So in the last video, right, we have learned about Bert, right? We have learned about the intuition and the details behind this model called Bert. So we have looked at how we can fine tune language model, which is already trained on huge language data, right? With and we could just use this knowledge. We could just transfer this knowledge to make this model uh, perform different other tasks or different other NLP tasks. To be precise. So to recap, right? BERT is a model, right, in which we have two stages, right? We essentially have a pre-trained model, so that is exactly what BERT is. But in overall, BERT is going to have like two stages. We are going to follow two stages. One is a pre-training stage, and another is a fine-tuning one. Yeah, so we have looked at the changes. So we'll be first pre-training this BERT model. So we have a specific architecture which is combined with masked language model, right? We have like rather than just predicting the next word, we will create a bi-directional architecture by making the model fill the gaps rather than just predict the next word, such that the model can not only understand the relation between the current and the next word, but also the relations in both the directions, which is definitely very useful while generating new images, right? So that is the main thing of BERT, and we could just use this pre-trained model. So we could just train this model on huge amounts of data, let's say on just random sentences. We could just make the model make the sentence. We could just take the sentence. We could randomly make like make some words as complete, or we could just randomly cut some words and make the model predict that those words in during that phase of the pre-training. And during the phase of fine-tuning, we could use this knowledge. So the model, after pre-training, the model will have a very good knowledge on the how text looks like, and we could use this knowledge on a different data set for a different problem, let's say question answering problem, or even text classification problem, or even any type of NLP problem that is related to language. And this is the very pretty individual and pretty good way and pretty useful way to use the pre-trained knowledge to of course solve different other problems in the field of NLP. And that is like the main thing that I've said. And also we will be using like we'll be concatenating all the sentences into like one single encoding, and we'll also not only learn the relation between the specific words in one sentence, we'll also at the same time learn the relation between sentences which are, and in the training data set, of course, we'll have sentences that come next to each other, and so that the model can learn not only how words connect but also how sentences connect, right? So that is the architectural things. And also while fine tuning, we'll have a final layer on top as per the specific problem that we are solving. So as you have seen, as you have probably seen in the description, or the title, or in the title and the thumbnail of this video, the main goal of this video is to just go through some code that have been in which we will be building a BERT. So we'll be just using the pre-trained BERT. So we'll have a pre-trained model. We'll load a pre-trained model from the transformers library. I hope we are comfortable with the transformers library. We have used that a couple of times, I think, in the previous NLP implementation, right? We'll be using the transformer library for like getting the model. And then let's just go through the code. I think I'll put the code in the description in the GitHub. So make sure to maybe open it up, maybe run it on your like run it. Just if you want to, you can just run the model or run the notebook. So yeah. So the first cell, we'll be importing TensorFlow, and we'll also be setting everything ready to use the GPU. So as we are using, I think, yeah. So we'll be setting up GPU. So just make sure that you have selected GPU here, just so that you could use the power of GPU while training the model, while like fine tuning the model. Right, I'll just click on run all, runtime and run all. So here the second cell is also doing the same. So we'll be importing type PyTorch and making sure that Python, and just commanding PyTorch to use the GPU that we have that we have, right? So we'll be doing that in the second cell. So if the GPU is available, we'll just run this. If not, we will just change the device to CPU such that we could use the CPU if there is no GPU. After that, we'll install the transformer library. I hope you are. I hope you have even just. I hope you know about transformer library. So transformer library is a library in which like it contains many pre-trained language models and many models that we'll be needing in regard to language modeling. So it is a very good library. So we'll just install it in order for the current use, and then we'll also be installing like the wget library through which you could access like because we could just download things online like from the Python environment. So now, so this is the dataset. Like at this link, you could get the dataset. I mean, if you just copy this link and paste it on your web browser, automatically the download will get started, right? Please 1 second. I'll save it. So and that is the thing. So we'll be downloading the dataset from this link, right? I'm going to call this wget function dot download. We'll pass the URL and the pass the like the and pass the location in which we want to save the dataset. So this is going to be the location, or this is going to be the address of this downloaded dataset. And we'll also unzip this. Remember, we'll be downloading the zip file, so therefore we'll be unzipping it to access all of the files, right? And the main file we will be reading is a data set. It's nothing but data set. So we'll just call the pd.read CSV. So pandas has a function called, or attribute called read CSV, through which we could like read and get, we could just create a data frame and read all the elements, or read the data in a CSV file. So again, we'll just input the address of the model of the data set, and we would just pass in some parameters such that delimiter equal tab. So here we are not having like CSV data, we are having TSV data, in which data is not separated by commas, but it is separated by tab spaces. So therefore we'll specify the delimiter is the tab. So this is the tab, that is just a space, and we'll be having no header. And so these are the columns that we'll be creating, right? In the data frame, we're going to have these columns, and if you run it, there are like 8,551 training sentences, like for this problem. Well, we are fine tuning the model, remember. And then if you look at like the first 10 rows, or the first 10 rows, or some random 10 rows. So this is how the data looks like. We have a sentence and we have a label, right? And these are essentially the pretty much the most important data that will be leading to fine tune the model. And then what we'll be doing is, as we only be needing this label and the sentence, we could just extract this label and sentence, and have a pretty neat data set, neglecting all the other columns, right? And then if I and then now, so until now we have prepared a data set, right? We have prepared a data set to fine tune the Bert model. So hope you understand what is going on here. We're going to download the TSV file online using a wget function, wget.download, and then we'll be converting them to a data frame, and then we'll be getting the most important columns, which are sentence and labels. Essentially, those are the two main columns that we'll be needing. And again, here in this specific problem, I don't think I have mentioned the problem that we'll be solving. So we'll be having what we'll be doing is, we'll be using the pre-trained BERT model. So the BERT model is actually trained on multiple information on the internet data. Again, as this is built by Google, uh, they have a lot. They have access to a lot of text data, so therefore they'll use model to train on that data. And then we could use this pre-trained model for this fine-tuning task. And this fine-tuning tasks, the current task that we'll be solving is a text classification task, in which we will be given a text and will be predicted label. I think we are solving like something like maybe something like toxicity or something, but it really doesn't matter, because our main goal is to group this data. Doesn't matter how they are grouped, but to make the model learn the differences, right? So this is the data set, and again, I should remember that the training is going on, right? So after we have done this, we could just get the pre-trained Bert model. So the Bert model is already pre-trained, right? So from this transformers library that we have downloaded or installed above, we could just get the Bert tokenizer. So this is exactly the tokenizer, not the model. So we'll be having a tokenizer in which we could just tokenize each word. So each word we will have a specific token, and from the data the Bert is trained on. So based on that, we'll have we will tokenize the current words also. So if you just run it, we'll be downloading the tokenizer essentially, right? And then now we could start tokenizing the values, and I'll just create a variable called, or we'll just call this method on this specific name, tokenizer, and then we could just use this tokenizer to encode our sentences, right? So again, we could just see an example. So let's say we have this sentence: our friends won't buy this analysis, and let alone the next one we propose, right? And if we could just look at this tokenized version, right? So this is the tokenized version. I think like in a list with each word separated. And then if you look at the IDs, so these are the IDs that are specified by the model. So each word is represented by a unique number as per the data set. Of course, the Bert model is actually trained on. And then if you look at and so this is the example of tokenization. And in this cell, right, we could just look at please excuse me. All right, sorry. So now we could just sorry. Mouse is not working. So as you can see here, in this in this specific code cell, right, we'll be using this I think, yeah, we'll be creating all the sentences, right? We will just essentially store all the sentences in this variable called sentences, right? I think that as a specific data frame, or any data storing quantity. So we'll be just looping through all of these sentences. I think sentences is a list, right? We'll be getting the IDs, and we could just look at the max sequence length, like each like what is the maximum number of words each sentence has. So that is 47, right? So yeah, that is 47. So we have 47 words. So the maximum number of words each sentence can have is 47. And then now in the next cell, we would just we just until now from the beginning we have treated like pre-processed data set and also initialize the tokenizer. Now it's time to tokenize our data set. So therefore we'll just use this cell in which we'll like create input IDs, attention masks, right? So here we'll just loop through all of the sentences, right? So we have a lot of sentences, right? uh we have essentially stored all the sentences in this variable called sentences. So essentially we'll just call this encode plus, we'll just call this encoder on this on each sentence, right? In this for loop, we'll just call this on each sentence and store that in a variable called encode and dict, right? And then um, we would just have this list input IDs, and then we'll like upload, and then we'll upload all the input IDs to this input. We'll upload all of the encoded version to this input ID. So essentially, we're going to have like a list of lists in which each list contains all of the tokenized elements for each word in every sentence. And then we'll also do the same for the attention masks. So essentially, we'll just we just get this encoded dict and the attention mask. So we also have this attribute to actually call the attention mask, right? Creating attention mask using this same tokenizer. So that is actually pretty cool. And then we could just have, and then after this for loop, we could just have input IDs and attention mask. So input IDs can consist of all of these tokenized values of each word. And then as you can see here, so the max length is going to be 47. So therefore, every word after or yeah, so every word after the actual sequence length is going to be 0 up to 47, just to make sure that every word has like equal length, right? And then here we could actually create the tensor data set, right? We have a data frame or a list. So now we will be creating a tensor data set such that we could actually train the model, right? We'll just call the data set. We'll be splitting the values into training and testing data set using the random split function. And then we could just call the data loader function to load this data into this specific variable, and we'll be creating this data into batches such that we could do batch wise training as it is better, right? So yeah, we have completed tokenizing the data. We have completed, creating like these data set tensor data sets. Now we could create the model. We could call the actual pre-trained model. So we have this pre-trained model, right? Again, from the same transformers library, we would import these three methods: Bert for sequence classification, Adam optimizer, and Bert configuration, right? So what we'll be doing is, so this is the main model. So this is the main pre-trained model. So this is the main pre-trained model. And then I'm going to say dot from pre-trained. So we can just call this already pre-trained model using this specific line or this specific part, right? I'll just say model is equal to, I'll just call this specific class or method, and we'll just say dot from pre-trained. We'll import the type of model we'll be needing. Again, we have a lot. They have a lot of documentation on different models, so you can just look at all the hyper parameters if you are interested. And then, rather than, we don't like in this case, we don't have to specify a output layer. Right, so we could just take the you could just use the specific like whatever model you want, and then we don't have to specify the output layer. In this case, you could just specify the number of labels. So as we are doing like zero binary classification, we have two possible labels. We'll be splitting the data into two possible classes, and then we will not be needing any output adjustments. We'll be not be needing any output hidden chase. Like when you want to build like separate models on this Bert model, you might want to make this as true. And then as we are doing like multi-class classification, we have the facility to directly specify the number of labels we want, and we would automatically have the final layer also inserted there for us, right? And then now I think we have already run this. So this is the architecture. If you want, please take a look. We'll be having like attention layers, many self-attention layers, many intermediate layers, maybe linear layers, and layer normalization. You can just go through the architecture if you're interested. So these are like the, so we have we'll just look at the layers we have. So you can just look at all the shapes. So the embedding layer. So this is the embedding layer. Again, we will be having tokenizers, right? You might remember that embeddings capture much more higher relationship. So therefore, we'll be creating an embeddings, through which you could represent the word much better, or represent language much better. So therefore, we'll be having that. And then, so this is the first transformer, right? We'll be having like these are the shapes 768 by 768. The bias which is going to be 768. The weights 768. So essentially, you could just look at all the shapes. So these are all the layers in the BERT model that we have imported from the transformer library. And then we could specify the optimizer we want. We'll be using Atom optimizer, right? We could just create an object, and then we could just now we would specify. Now it's time for us to start training the model. We'll specify the number of epochs, the number of total number of training steps, and we'll be creating a scheduler, right? We'll also be creating a scheduler, and then we'll be creating an active accuracy function to calculate the accuracy, right? We'll be having the parets and labels. So essentially a very simple process. We'll just look at the number of correct by predictions by the number of labels, and then we'll just like get the to calculate the amount of time. We have built this other function also to get the time, and then yeah, so we will be start training. So this is the training function. So we'll be importing random and numpy, and then we'll be setting a random seed to for reproducibility, such that you could again when you run this you'll get the same values, whenever we use the random function. And then this training stats, we'll just creating a list, and then we'll just start the timer, right? And now we have to actually start the training loop. We could just start the training loop, and we'll loop through up to a number of epochs. We'll just create the time. We could just start training the model. We could just loop through all of the data train loader, right? We could just call this, right? We have the batches. So we're gonna have like steps and batches, right? We are going to like store them into these variables. We are going to pass these values. So we are essentially going to pass all of the tokenizers, and we're essentially going to pass the tokenizers, the labels, and the mask to this model, and and we're going to calculate the loss, right, based on this output of the model, and then we are going to add the losses. We are going to do the backward propagation to update the parameters, weights, and then essentially I think this is like clip grad norm. What is it? Yeah, so we'll be clipping the gradients. So remember, just to make sure that there is smoother training, we clip the gradients up to this threshold of 1.0, just to make sure there is no like too much amount of like instability in the model. We want the model training to be stable, so we'll just clip these gradients to a specific threshold, and then we could just call this optimizer.step and scheduler.step to start training the model. And after that, right after so after that we could just calculate the training loss. So we'll be having the total training loss, which is going to be the sum of all the training losses in each step, in each epoch. So therefore we'll be getting that, and then we'll be calculating the training time, average training loss, average training epoch took. So essentially this is like each training epoch we'll be doing that, and then we'll be again looping through the batches in the validation data set. After training the model, we'll be also using this trained model using the updated parameters on the validation data set, right? So we'll be looping to the validation data set and using the same model to essentially doing the same, right? We are just not going to update our parameters now, and then and that's it. We'll just print the accuracy, and we could finally print that the training is complete. And as I'm talking with you, the training is already over, and it just took like 5 minutes. It just took 5 minutes, which is like pretty good. If you want to train a model from scratch, and even to solve this problem, it might take a little bit more time, and you might get a little less accuracy. But here, it is fast. The model is pretty fast. And then if you look at the accuracies also, it seems like it converts good, but the validation data set loss is quite increasing, not quite converging. So maybe we want to use like some overfitting or regularizers, maybe more regularizers you might want to use. But overall, the performance was pretty good. It was fast. Model training was fast, and of course, it is going to be better than a normal model, right? And we could just and I've just put some more uh and there's just some more code to save the model, save the pre-trained model, and save the current model essentially. So yeah, so that's it for this video. You know, I think we have. I think after this video, you have got a fairly good understanding of BERT and how it works, how we can fine tune it for our specific problems, and of course, you can like fine tune your own model on your own data set, whatever data set you want to fine tune it on. So thank you for watching. I'll see you in the next video. So yeah.